Let's talk about determinants. So let A be a square matrix. We'll denote its entries Aij as usual. We're going to introduce this notation capital A sub ij, and this is going to mean the n minus 1 by n minus 1 submatrix you get by deleting the ith row and jth column of A. So for example, if I take this 3 by 3 matrix here, then A11 I'm going to get by deleting the first row and first column of A, and I get this 2 by 2 matrix 3, 1, 4, 8. If I look at A32, I'm going to delete the third row and second column of A, and I'm left with this 2 by 2 matrix 1, 7, 2, 1. Okay, so that's the notation we need in order to define a determinant. So again, A is our n by n matrix. The determinant of A is defined recursively as follows. So if n is 1, so that A is just this entry here, a 1 by 1 matrix with entry A, then the determinant of A is just that entry A. If n is bigger than 1, then the determinant of A is this alternating sum. It's a sum j equals 1 to n minus 1 to the 1 plus j, a1j times the determinant of that submatrix where you delete the first row and jth column. So let's copy this formula over again here and compute an example. Let's take a look at the 2 by 2 matrix 5, 7, 3, 2 and compute its determinant using the formula. So I grab the 1, 1 entry of the matrix, that's a 5, times the determinant of the submatrix where I delete the first row and first column, minus, now I'm going to grab the 1, 2 entry, which is a 7, times the determinant of the 1 by 1 submatrix where I delete the first row and second column. And then I just compute and see the determinant is minus 11. Now this will work in general for a 2 by 2 matrix. The determinant of AB, C, D is AD minus BC. And you'll recognize this formula from when we were looking at inverses of 2 by 2 matrices. Let's use the formula in a slightly larger example. Let A be this 3 by 3 matrix here. Then the determinant of A, I'm going to grab the 1, 1 entry, which is a 0, multiply it by the determinant of the submatrix where I delete the first row and first column, minus the 1, 2 entry, which is a 5, times the determinant of the submatrix where I delete the first row and second column, plus the 1, 3 entry, which is a 1, times the determinant of the submatrix where I delete the first row and third column. Each of these 2 by 2 matrices I can compute using the formula, and I see that the determinant is 2 after I'm done with the arithmetic. Now, I'm going to introduce a little more notation so we can state a result. We'll let Cij be the ijth cofactor of A, and this is a scalar defined to be minus 1 to the I plus j times the determinant of the submatrix you get from A where you delete the ith row and jth column. Okay, and so the result is that you can compute the determinant of A by expanding along any row. So if you look back at how we were computing the determinant, we were sort of expanding along this first row, grabbing the coefficient from the first row, and then deleting the first row and some column, right? And so this is saying that we can compute the determinant along any row. So if I fix the ith row, then the determinant of A is the sum j equals 1 to n, aij times this cofactor. Similarly, we can compute the determinant by expanding along any column. So if I fix the jth column and say I want to expand along that, then the determinant is the sum I equals 1 to n, aij times cij. And so we can use this to our advantage, right? If you notice a lot of 0 entries in the matrix A, either in some row or some column, 0 times the number is very easy to compute, and you're going to use this to shorten the by hand computations you have to do. All right, so let me say a little bit about the minus 1 to the I plus j pattern. So minus 1 to the I plus j, if you notice in the 1, 1 slot, I plus j is even, and so minus 1 to the I plus j is plus, is positive 1. If I increment either I or j by 1, I get a minus. If I increment again, I get a plus. And so you're left with this checkerboard pattern of pluses and minuses. And this will help you in case you get stuck on the minus 1 to the I plus j. So let's take a look at example 3 on page 166 in more detail. So I want to warn you, the textbook, at least in the 4th edition that we're using, it's misleading because there's an error in the signs. They put in some minus signs where they don't need to put in minus signs. It ends up being computationally the same because they put in a minus 0 instead of a plus 0, but it is misleading in the text. So suppose A is that matrix given in example 3, right? So it's this big 5 by 5 matrix, and I want to compute its determinant. And I notice there's lots of zeros in column 1, and so that's the column that I'm going to expand it along. I grab the 1, 1 entry, which is a 3, and it's 3 times the cofactor C11 plus 0 times the cofactor 21 plus 0 times cofactor 31 plus 0 cofactor 41 plus 0 times cofactor 51. Right? So I'm expanding along that first column. So from now on, these 0 terms, we're just going to omit to simplify things. Okay? And so now let's just continue computing. So this 1, 1 cofactor, it's the determinant of this 4 by 4 submatrix here. And to compute the determinant of that 4 by 4 submatrix, well, I notice that there's a bunch of zeros in the first column again. I'm going to expand it along that first column. So I pick off the 1, 1 entry, expand along that column, and I have the 3 by 3 submatrix here. And notice I'm omitting the other terms, the 0 terms. And now I'm going to continue. Let's expand. I get a 1 times the determinant of this 2 by 2 plus, minus a 5 times the determinant of that 2 by 2. Right? So there, at this stage, I'm just expanding along that first row. The 2 by 2 submatrices I can compute using the formula from earlier, and so I get that the determinant is minus 12.